Hey Mohammed, so I was reading up on the latest in EV batteries and it's wild. Like totally not what I expected. This whole quantum computing thing, it's not just a buzzword here, is it?
Emma, my friend, it's absolutely not just a buzzword. It's a profound paradigm shift, really. For so long, EV battery development has felt a bit like, well, educated guesswork, like trial and error in a lab, tweaking chemistries. But quantum computing, it's changing the very foundation of how we approach material science for batteries.
Okay, so when you say profound shift, what does that actually mean for the industry? Are we talking about like making batteries that last longer or charge faster? Or what's the big deal with, simulating at a quantum level?
Precisely. It's all of that and then some. The thing is, traditional computers, as powerful as they are, they hit a wall when you try to model the subatomic world. And batteries, Emma, they are inherently quantum systems. Electrons, ions, chemical bonds, their true behavior, it's at the quantum level. So with quantum computers, we can actually simulate these interactions with stunning accuracy. It shifts R&D from that trial and error to predictive precision. It's a huge step forward for novel chemistries and just optimizing everything.
Wow, predictive precision. That sounds like almost magical. So, what does that look like in practice? Like, are there any specific examples where this quantum approach is already making a difference in finding new materials?
Oh, absolutely, Emma. It's not science fiction anymore. It's happening now. Take, for instance, the joint project between Volkswagen and Google. They actually simulated battery materials on quantum processors. Their goal? To create a tailor-made battery blueprint, you see. The result was just phenomenal. Faster exploration, significantly fewer dead ends in research, and an accelerated path to getting market-ready innovations. This means we're moving towards solid-state, lithium-air, sodium-ion batteries, those next-gen chemistries, much quicker.
That's incredible. So, it's not just about like discovering completely new elements, but optimizing existing ones too. I guess, what are the direct benefits we'll see as consumers from these kinds of material breakthroughs?
Exactly. It's both. We're talking about designing materials with higher energy density, Emma, which means longer range for your EV. Then there's thermal stability, much safer batteries, less prone to overheating, and crucially, faster charge rates. Imagine plugging in and getting a significant charge in mere minutes. It really slashes R&D timelines and costs, which eventually means more affordable, better EVs for everyone. It's truly revolutionary.
Okay, so faster R&D and better batteries sounds great. But like is quantum computing just for the chemistry side of things or is it impacting other parts of the EV battery life cycle too? I'm thinking about manufacturing and, even once the battery's in the car.
That's a fantastic question, Emma. And the answer is a resounding no. It's much broader than just chemistry. Quantum algorithms are also being vigorously explored for manufacturing and supply chain optimization. The EV battery supply chain, it's incredibly complex, full of bottlenecks. Quantum can solve multivariable optimization challenges, from reducing defects during production to managing materials more efficiently. Think improved process reliability, higher throughput, smarter inventory, and lower costs. It's truly comprehensive.
Wow, so it's like making the whole system smarter. And then when it comes to the car itself, like how it charges and uses power, is quantum involved there too?
Precisely. It's all about smarter systems, Emma. We're talking about smart charging and energy management. As EVs become mobile power sources, smart charging needs to coordinate dynamically with the power grid, you see. Quantum algorithms can create grid-aware charging systems that prevent overloads, optimize charging schedules for entire fleets and cities, and ultimately provide an enhanced user experience with minimal infrastructure strain. It's about making our energy future more efficient and resilient.
Okay, so This is huge. And it sounds like something countries would be racing to get ahead in. Are we seeing a global quantum enabled battery tech? Like, who's really leading the charge, in this space?
Oh, Emma, it's absolutely a global race, and it's heating up significantly. It's not just about who builds the fastest quantum computer, it's about who applies it first and best. The United States is, seeing partnerships like Hyundai and IonQ, Ford and Quantinuum, with strong support from DOE labs. China, they're investing heavily through Alibaba's Damo Academy and state-backed research to solidify their EV dominance. Germany, with Volkswagen and Google and the Fraunhofer Institutes, they're early movers too.
That's a lot of big players. And what about like other regions? Are they all focusing on the same types of applications or are there like different strategies?
It's fascinating, Emma, to see the varied approaches. Japan, for example, with Riken and the University of Tokyo, they're exploring theoretical models for topological quantum batteries. The UK has Spacecraft, Johnson Matthey, UCL, and the University of Sussex focusing on realistic simulations and quantum sensors. South Korea's national quantum strategy and Hyundai's partnership with IonQ are blending their EV leadership with quantum infrastructure. And Canada, my home, is a quiet force with Xanadu and the National Research Council leveraging photonics and robust academic industry symbiosis. This isn't theoretical, it's hybrid, it's accelerating, and it's a national strategy for everyone.